In this work, we developed a knowledge-based AI agent, IKBT, to solve symbolic inverse kinematics. Inverse kinematics, or IK, solves the problem of how to control robot arm joints to achieve desired end-effector positions and orientations. This is critical to design and control any robot. In other words, inverse kinematics maps a transformation matrix to joint variables. It is a common misunderstanding that closed-form inverse kinematics analysis is solved. Popular software and algorithms, such as gradient descent, claim to solve IK problems, but only on the numerical level. While the numerical solutions are relatively straightforward to obtain, this method often fail even when the IK solutions exist. Therefore, closed-form IK analysis is superior, but there is no generalized automated algorithm because of the high-level logical reasoning involved, and is generally handled by human experts. We developed IKBT, a knowledge-based intelligent system that can mimic human experts' behavior in solving closed-form inverse kinematics using behavior tree. Here is an example symbolic inverse kinematics problem. The left-hand side denotes desired end-effector position and orientation. The right-hand side is transformation matrix containing symbolic expressions with unknown variables. The goal of inverse kinematics analysis is to solve for these unknown variables. In this example, there are θ1, θ2, and θ3. We'll start with the simple equation labeled with green box, R31 equals to minus θ2. With trigonometry knowledge, we know that solutions for θ2 is arcsine minus 31 or pi minus arcsine minus R31. θ2 is solved. Next, we move on to the orange equations to solve for θ1. We can divide these two equations and get tangent θ1 expression. From that, we can get θ1 by a tan 2 function. Similarly, we can solve θ3. At this point, you probably think that symbolic inverse kinematics analysis is not so bad. I'd like to remind you that this is just a toy example. What people usually deal with in real world is an equation like this. This is a typical symbolic inverse kinematics problem, where the expressions are too long to fit into one line, and it often needs to be displayed column by column. Though the solving process is similar to the previous one, this is a much more daunting process. Knowledge and rules used by engineers when solving closed-form inverse kinematics are encoded as action leaves in behavior tree. The order of applying these rules is governed by higher-level composite nodes such as selector and sequence, which resembles the logical reasoning process of engineers. Because IKBT explicitly uses common knowledge that engineers use when solving inverse kinematics problems, such as trigger identity or the method of determinants, rather than relying on tricks for specific kinematic configurations. IKBT can solve most serial chain robot arms without assumptions of configuration or the degree of freedom. And because human knowledge is encoded as leaves, this modularity makes it easy to extend and modify IKBT's toolbox. IKBT searches and applies suitable knowledge or rules to equations containing unsolved joint variables as human experts do. In the process, IKBT not only provides a solution, it also records the applied knowledge, making the results easy to understand. This human interpretable strategy provides a way to validate the AI's decision-making process. Unlike numerical methods that usually stops when one solution is found, IKBT finds all possible versions of solutions. Results from IKBT are put through a verification process, where we supply a set of numerical joint variable values and perform forward kinematics, which maps the joint variable to transformation matrix. Then plug the numerical transformation matrix content back into the symbolic IK results from IKBT. Test 1 is to confirm one set of the solutions should match exactly to the input test value. The second test is to take the numerical solutions and perform forward kinematics. The resulting transformation matrix should match exactly to what we start with. IKBT tracks joint variable dependency, which is critical in obtaining the correct combinations of different versions of joint variables in order to achieve desired position and orientation. IKBT was tested on multiple robots, and it solves most of them regardless of their configurations or degree of freedom. These test robots include commercial robots such as Puma 560 and popular robot UR5. On top of that, IKBT automatically outputs IK solutions in LaTeX, Python, and C++. Code available at UW Biorobotics GitHub. To summarize our contributions, IKBT is the first automated generalized AI solution for symbolic inverse kinematics analysis. It solves most serial chain robot arms without assumptions of configuration or degree of freedom. It tracks variable dependency and generates solution code automatically. IKBT explicitly uses common knowledge that engineers use when solving such problems. It searches and applies suitable knowledge or rules to equations containing unsolved joint variables, as human experts do. Because of that, the solution generated from IKBT can be easily interpreted by human engineers.